What I'd like to do today is to go back to this leash S4 example we did, which we didn't finish last time, and I kind of want to review the first part and then go through the last part, which I was rushing through at the end. I did want to mention one thing that at this point, I'm going to make a decision this weekend, but I'm likely going to give you a third homework on doing in S4 methods, which your current homework is in S3 methods. I say that I'm probably going to do that because in order for you to be able to have some reasonable chance of doing it, I need to do one more example on something that's a little more similar to what we'll be doing. So when I did the S3 assignment, I had done two examples. I did a t-test and I did the lin mod. And so I'm going to look at least one of those two to redo probably lin mod using S4 classes, and then that will be reasonably similar to what you need to do on one way. So if I work through that and do that, then that's probably going to be a third assignment. Otherwise, the other option is to give an assignment on these little snippets of code that come from the book. I just don't happen to think that that's sort of the optimal way to do. I don't think you learn programs by looking at little pieces of code. You have to look at it from the big picture conceptually to understand. And the idea of working these examples of S3 is to try to give you a bigger picture of the way it works. And so that would be a criticism of this book, but it also tends to be a criticism of the relatively few other books I've found with S4 methods. There are two of them. One of them is by John Chambers, and I don't remember if I referenced that. I perhaps didn't. But he's the guy that wrote a lot of R, including S4 classes. And he's also the one writing a new class system called R5. And he's coming out with another book. But his book is pretty technical, perhaps even more technical than this book. The other people is, I think it's Venables and Ripley, have written a book on what they call S programming. And I believe they also give some S4 examples. I have to take a look at it. But again, I'll probably just try to redo one of the examples that we've already done so you can say, okay, this is what it looks like in S3 and this is what it looks like in S4. Now technically there are ways to convert S3 classes into S4. And if you had a big project, that's probably what you would want to do, but then that doesn't necessarily tell you how to develop S4 classes. One of the reasons that S4 is more like a more formal programming language, more like Java, C++, and so forth. I say more like because R takes the point of view of, and I would describe R as primarily a functional programming language. So the question is, in other words, everything in R is basically a function. And you can operate interactively at the terminal by giving functions and you get results back immediately. That interactive nature is a very powerful aspect of R. And so you don't want to give that up, but at the same time, if you have big projects, you need to have a structure that's more formal than just writing lots and lots of functions. If those of you that have taken SAS, it's very, very difficult. It's very difficult to program new procedures in SAS, and so some people use as a proc matrix as a matrix procedure, and it basically allows programming more than just the data management aspects, which is what you do in the data step. it lets you program using matrices, and so you can do a lot of things, but the problem is it defines everything at the global level. And so you could never really, using the matrix procedure in SAS, you could never really program something very complicated. You don't have the internal structures, you don't have the rich data structures, you don't have the encapsulation within environments and so forth. And so you really couldn't use SAS to do the types of stuff we're doing here. And programming, you can write your own procs, but again, it's uncommon for people to do that, because you have to get into the internals of SAS. And so almost all the procs that exist are written by SAS. And so, and that's sort of a problem with both SAS and JMP is, if you're doing research and you come up with a new theory, you need to test it out on data, right? Well, that's why almost all academic statisticians use R, is because we have to write, we have to write code for new methods that we develop, and we have to test it and so forth, and maybe do simulations on it and so forth. So that's why almost all academic statisticians use R. It's not to say that some don't use SAS, but SAS is more heavily used, in the pharmaceutical company and government, financial industry, and places like that. At any rate, so I'm going to go back through this leash. I'm now in the leash notes of chapter 3 of the notes for 523, and you do have these notes, and I don't think I've changed these notes. I just wanted to review what we were doing. We were taking what was called a PIX map, and that was the main class, and then we were subclassing it into an index type plot and an RGB type plot. So we were subclassing it into two classes, and so we'll go through that. And then the image procedure needs an index plot, so we're going to learn about coercion and things of that sort. So step by step, we're sort of getting there, but even this example, together with the other one, doesn't quite give you what you need for a computational example like the one-way, which isn't that difficult, but again, the way we approach the one-way will be a little bit different than the way we're approaching this. But again, this builds up the idea of what we're doing. So let me set the working directory, and let's sort of see if there's anything in the workspace. No, it's empty. You can get in trouble if you have stuff in your workspace. So I'm going to define a new class called PixMap, and it has 3 slots: size, cell resolution, and bounding box. And these are the initial values we're going to give it with the prototype. So we'll do that, and you can see the initial values. And then I'm going to define the 2 subclasses. Notice that PixMap RGB contains PixMap, means it inherits from PixMap, and it has 3 new slots. It doesn't have to repeat the slots that you defined above because it inherits those slots. And so when I do this, I can see that well, I'm not printing out the slots at this point at least. And then I'm going to do an index method, which depends, instead of RGB, it's going to depend upon a matrix of color values. And then you have to give it the color values. It's going to do it more as it's going to have these colors in a matrix. And so I'm going to set class for that subclass. And let's create I'm going to create my pick, which is a new index map. And then if we look at it, by default, it's not printing out the new slots, but we can actually create a we can define values for these slots, and at this point we can directly use the accessor functions. So I haven't defined the values for the index, the color, or the size. So if I say the index, which is a matrix, is going to be a 4x4 matrix, so 1:16 with 4 rows and columns that would give. So I'm using the at, my pick at, that actually defines that slot, which hasn't been defined yet. And then the color is going to be defined from this heat dot colors, and the heat dot colors are used in heat maps from hierarchical clusterings that are often done in genomics and bioinformatics. So I'm going to define the colors as just 16 colors from the heat map, and I'm going to define the size will be based on the index. And then if I look, we see the size is now 4 by 4, whereas previously it was 0 by 0 because that was the default values. Okay. But suppose we want to see everything. So I'm going to do a show method for pixmap, and that can be inherited for the other methods. But actually, no, we're not defining the RGB or the index values here. We're just defining it. I'm not going to spend time going through this again because we went through this in some detail, but I'm going to concatenate the type with the, if I do, I want the class of the object that I'm going to be creating, and then the size of the object, and I'm going to collapse it with a times, and then the cell resolution, and then the bounding box. So this is sort of printing this is creating our own show method. And okay. I'm also going to define a plot method for the index plot. Now remember, this defines the method, and this defines the signature. The signature says this is a plot, but it's of type pixmap index. So that when this plot function, when I give a plot, it will be of type pixmap indexed. And if you actually this is creating a generic function. You may say, well, I didn't say set generic, but the reason is this plot is already a generic function from the main packages of R. Plot is already a generic function, so I'm sort of adding to it. You might ask, what is all this stuff? This looks rather complicated. Well, if I pass it, let's just let's create a new pixmap, and then is my pixmap, which we had defined before up here, and we had defined the slots. And if we plot this, we get this heat map. So where did these colors come from? Where they came from is that if you look at this argument x at index x size, so we might first of all sort of see if we can do my pick at size. So it's 4 by 4. So what happens if I now add a 1 here, which is what's done up here, okay? Then that's simply bring the first argument, which is 4. This is 4 by 4, so it's pixed to 4. And what happens is you sort of keep adding to this. If I now say I want an index of my pick at size, and then I want 1:1 we might see what we have at this point. Let's see, index. Oh, I'm sorry. I have to do my pick at index. Okay, so that's 4321, and if I if I continue this, and in other words, I'm building up this sort of step by step. So if I Control A and say I want the transpose of this, and I'm going to now create a color which is equal to my pick at color. Let's see. No, that's actually, I want to do this. I want to put the parentheses here. Okay. That just transposed it. What's going to happen is, though, it's going to get expanded out to a 4x4. But this is sort of the logic when you do an image based upon that. And I think, let's see. Trying to remember. Wow. This defines the color. There are no labels on either axis. In fact, there are no axes, and the aspect ratio is 1. Otherwise, you wouldn't get that nice square graph. Before I had gotten the matrix that was 4x4, and I don't seem to be reconstructing that now. Obviously, it does. But I'm not seeing how to do it. It actually constructs it, and the first column is like 4, 3, 2, 1, and the next column is like 8, 7, 6, 5, and the next column is similarly. And I'm not quite sure exactly how it's getting it, but it obviously does. But I don't know too much about this image function. I haven't used it that much, but at any rate, it did obviously give you a 4x4 if I look at the plots. Okay. So this was the 4, 3, 2, 1 coming down, and then I'm not quite sure how the image is sort of segmenting it down, but I think what's happening is when I say x.color, and color is the way we define the color, it's 16. I think that it picks out the 4, 3, 2, 1, and then it uses what's called vectorized arithmetic, and then it picks out the next 4 and the next 4 and the next 4, but in reverse order. So I think that's what I mean by vectorized arithmetic. So if you have a vector of size 16, which color does, then the first time it picks out, and I reverse the order, it picked out 4, 3, 2, 1, and it picks out the next 4 in reverse order, the next 4 in reverse order, and the next 4 in reverse order. And I think that's what image is doing. It's using vectorized arithmetic to get each column, sort of column by column. I believe that's what the image function is doing. At any rate, it does seem to work. And the image function can give you very, very high resolution graphics, and a lot of times in high quality publications you can use this image function to create very high quality graphics. So let's look at the slot names of pick maps. Now notice that, I'm not sure why I'm losing this over here. So notice that pick map is an index map, so as index color, these are the slot names. It has the 3 from the pick map, and then it has 2 more that are specific to that class, which is the index subclass. So it has index, that adds index and color also. And so what I'm going to do is I'm going to actually coerce pickmap into its mother class, or the class it inherits from. And let's see what happens to the slot name now. So now I'm coercing it to be pickmap class. And if I now look at the slot names, now I've lost these 2. It only has the 3 that are in pickmap. But now what I'm going to do is I'm going to create a new map. I'm going to create a new instance of RGB, but I'm going to use as its initial values the slots from pickmap. Because pickmap, my pick1 is now of class pickmap, and so what I'm going to do is create a new one, but it's also going to inherit these slots of my pick1. So let's do that. And now I'm going to do the slot names. And now notice that I have RGB. I have the RGB values, the red, green, and blue values, plus the 3 from the mother class pickmap. Now, what I'm going to do, and I don't know for sure whether the image plot supports RGB. So what we're going to do is coerce an RGB type graph to a pick index plot. So this set as coerces from one class to another. So I'm going to coerce an RGB class to an index class. And I'm going to say, but I'm not 100% sure of this, the image class may only support it. Let's say the image class only supports an index type plot. And so if you've got an RGB graphic, and a lot of times you import stuff, if you import stuff from out on the web or whatever, and it comes in as an RGB, which is a very common type of format. So if it comes in as an RGB, it's okay, now I need to convert it to an index plot so that I can use image to print it. So this is what it will do. It will take the RGB parameters and it will coerce those into it will coerce them into the format we need for an index map. So that's what this set as. Now notice that it's set as with capital A, small s, and I've said this a number of times, but R is case sensitive, so you can't just sort of arbitrarily, if you're on Windows or something, the case doesn't matter, but that is not the case in Unix. So so that's what we're going to do. So RGB is a function, and we're going to, the from is where we're coming from, so we're going to use the access or the at to get the red, green, and blue slot values, and that's x. And if in fact some of them had the same values, then we would collapse them by using unique. That's not going to be the case here. And then we're going to create a matrix. We're going to create a matrix from this based upon the color, which in this case is what, 16? I printed out. I don't know if I have it printed out anyplace, but we defined it someplace. We defined it as a vector of length 16. And we match, and that may drop certain ones, and then we're going to, we're going to get the 2 size variables, and we're going to make it in a matrix based upon the first, the size components, which in this case will be 4 by 4, and then we're going to create a new pickmap index based upon this size and this index and this color. Okay, so that's what that function does. So let's run that. And then we're going to set a method. The plot method is simply going to coerce it. It's simply going to coerce it into a pickmap index. So if we send it a plot that's a method, it's going to, that's RGB. This is a plot method for RBG, but it's, in other words, I'm defining a plot method for RGB, but what we're going to actually do is coerce it into a pixmap image. So a plot method just coerces it. This isn't unlike what you did for like your homework. If you've got a factor and you've got one column that's the factor and one that's the values, you're simply going to use the factor to split it into vectors and then call the original one that's done in. If you do the original using one list for each sample, or one vector for each sample. It forms a list of vectors and one vector for each sample. If that's the default, and then you have a factor and a vector, then you sort of make a list of vectors from the factor, and then you call that original. So in effect, you're coercing it. But we did it directly. But here we're doing it for all RGB images are going to be coerced to the indexed. And then we'll use image to actually do the plotting. Does that make any sense? So if I import an RGB, what I'm going to do is I'm going to coerce it into an index plot and then call image. That's always going to happen because the plot method associated with RGB does the coercion automatically. Okay, so that's what we're doing here. We're coercing the plot. So now I'm going to define a sequence from 1 to 3 of length 100. So that just sort of takes 1 as the start and then 3, and then it divides it up into 100 slots, so it gives a fairly fine resolution. Of course, if you did 1,000, it would even be finer. But it would now be, since we're taking the outer product, this outer product is going to be a 100 by 100 matrix. If you did 1,000, it would be 1,000 by 1,000. And then we're going to define a function on the xy coordinates of this matrix, this outer product, that would be based upon sine and cosine functions. And this is taking the sine of x times the sine of y. It's taking the absolute value of that. And then that's z1. And then z2 is taking the sine of 2x times the sine of x. If you don't know your trigonometry, you can go back and review it. Then the sine of x plus the sine of 2y. So those are the z1, z2, and 3. And so I'm going to find a new RGB. The dimension of it is the dimension of z1, which will be actually 1,000, because it's going to vectorize it to get to the dimension. And then the red, green, and blue are going to be the z1, z2, and z3, but remember they're going to get converted. So did I do all these? No. So I'm going to define z1, z2, z2, and z3, and then I'm going to create a new instance of this. If I look at it, notice that it's an RGB, but now when I try to plot it, it's going to coerce it, and if I plot it, it's going to do this. So you can get some very pretty things. We simply used a blurring technique. The sine and cosine is a cyclic function, and the way it's, if you actually study the values that come out of this with the sine and the cosine, be a nice. If you try to write an explanation about why that image is coming out as it is, you would have to actually know a fair amount about the sine of x and the sine of 2x. And that type of argument and what that does, and what happens when you multiply signs and so forth. Now in R you can plot these functions. You can plot the function sine times the sine of y, or sine of 2x times the sine of y. So in R you can actually plot these functions. Now if you plotted it, you can do three-dimensional, in other words, you could do three-dimensional graphics in R that would have x on one coordinate, y on one coordinate, and you would. But in effect, when you take the absolute value, that's what we're doing, you see. This is a two-dimensional representation of a three-dimensional plot. But you could actually plot the sine and the cosine with an x, y, and a z, where z is the actual value. What we're doing, instead of plotting an x, y, and a z, we're giving a color color coding to the z-axis, depending upon the values. Do you understand what I'm saying? So we're defining a color based on the values of the z-axis. So this is sort of like a colored type contour plot, where you slice a contour plot, and if you gave every contour a different color, but we have to collapse it so we see it as a contour type plot. By the way, of course, or it does have a contour plot, and so if you had a mountain and you slice this mountain, and the mountain's sort of all over the place, but it's basically, let's say it's one mode or one top, and if you sliced it through, you would see these. If it's a normal, bivariate normal, and you slice it through, you just get the ellipses that get smaller and smaller until you get to the top and you have a single point, and then it disappears. So you have this series of decreasing ellipses as you slice an ellipse. But if you have a mountain slicer, it becomes very irregular. But you can do these types of contour plots in OR. And in fact, but rather than doing a contour plot, what you might want to do is something like this, is you colorize it. So given the intensity relates, the intensity of a certain color relates to the elevation of the mountain. So that's the kind of thing we're doing, and all of this can be done in R, by the way. So now, if I try size, if you go back and you look at my pick, and if you look at my pick. The size, notice, needs to be a matrix, and so if I try to, this says, okay, I'm going to take the slot, I'm going to reassign it hello, and you get this error message. It says you can't do that because it internally checks, and it internally checks and says it has to be. It has to be a matrix type object, and it's not, and so it's invalid. So this is one of the advantages of S4 programming, is it won't let you give bad values to the slots. It has to be, your slots have to be of the right type. It checks automatically. That is not true of S3 classes. You may reach an error at some point, but it doesn't do type checking. But suppose we want to check some other things. So we can write a set validity. We can write a function called set validity. It's sort of going to check the validity of the slots. So I'm going to do that. And so let's define this function. And if you look at this function, what we're going to do is check the bounding box to make sure that it's a correct bounding box. So this has to be a box that has a lower left and an upper right, and it has to have the correct boundings for that to be the case. Otherwise, if it's not a rectangle, it's not going to work. So you can have a problem with either the rows or the columns. So it's checking that bounding for both the rows and the columns, and it will give you an error message if in fact this is not true. Now, if I look at my pick, why did it not reassign the size to hello? It's still RGB. Oh. I'm not sure. Run this again. It didn't seem to change the slot value, but it's giving the error. I need to check on that and sort of see what's happening. If I give my box bounding 0011, let's see what happens. And let's check it. And that says 00100100 100 is valid. I think the way the bounding box is, if you think of a rectangle, in this case a square, the lower left would be the 0, 0 position, sort of at the origin, And a 100, 100 would mean 100 this way and 100 up. And so that defines a square. I think that's the way it's defining the bounding box. Now, if I say, there are just some access methods. So if I want to say, well, what is the, show the class of PixMap, and you can see that the class is PixMap, and it tells you the slots. And it says knowing subclasses, it tells you the subclasses. So that's fairly nice. If I just look at plot, I meant to be down here. If I look at plot, plot is a standard generic defined for the package graphics. In other words, there's a package graphics that has a plot as a function. So when you say plot, if I say plot x, where x is a vector, let's say, what will it plot? Well, in the base graphics package, if x is numeric, it will plot a histogram. If it's character, it will plot like a bar chart. But if I had x and y, so if I say plot x and y are both numeric, it plots a scatter plot. But so we can sort of look at what happens. Suppose x is categorical and y is numeric, then it will plot a side-by-side box plot and so forth. So in other words, it's already a generic function, and what it plots depends upon the arguments. So let's sort of see if we can change this. So if I say, suppose I said, I want the methods for a show. So if I do this, you notice that there are a lot of objects that have a show method for them. Now notice in particular, so if I have a diagonal matrix, it turns out that the matrix package is implemented as an S4 class. And therefore, since it is, then there's a show method for a matrix. So anything that's implemented as an S4 class, it usually will have a show method. And so these are the show methods that I have access to right now. But notice that someplace along here, notice these three. Those are the ones that we just defined the show method for. So we have a show method for PixMap, for PixMap index, and for PixMap RGB. Had we not done this little exercise today, they wouldn't have been here. They came from us. The rest of them were built in. Now, you might also want to say get method for show for PixMap. So if I do this, I'm getting the show method. This is the show method for PixMap, and that's what we had defined above. Okay, it tells you the signature and target and so forth. Okay, so in general speaking, if I want to set a generic, I'll set a generic. Like my generic would say, okay, I'm going to make a generic out of this. Now at this point I haven't defined arg1, arg2, and i3, and I'm not going to, but that's how you set a generic function. Then usually what you do is set a method for that generic function. And in the other example that I did, I actually set generics and I set the method for the generic. Because you can set a method and then you can well, I'll give you an example in just a minute. It might relate to the next homework. And then my generic says, okay, it is a generic, and presumably I can dispatch on arg1, arg2, and arg3. So if you create a one-way, suppose you create a one-way, and you're doing it in S4 classes, and you want, and you've got, let's say, two arguments, whatever, x and y, or let's say the arguments maybe are sort of the data structure and the data and the structure you're using. And so if you then say that one way is a generic function, then it will dispatch on the first two arguments. And so if the first argument is like a list of vectors of your values, and the second argument is missing, then it's going to sort of do the default method, which just basically does it on the vector of the list of the vector of your data, one vector for each sample. But suppose one is a factor and one is a vector of the numerical values. Then it will dispatch based on that and so forth. And so that's sort of the idea. But again, I'm going to sort of show you a little more detail. But if you were doing a one-way using S4, you would use these methods. You'd probably set one way as a generic function. And you're only going to actually write your code to do the one-way analysis of variance for one of those methods. And the one in the S3 classes, I ask you to do it as a list on a vector of the values. But and then typically what you would do is if you actually had a vector, if you had a vector of values plus a factor, then you take the factor and take the vector and convert it into a list, and you'd call that one default method and so forth. So it's not going to be as different as you think to do S4 classes. It's sort of the same idea. Now that's not how R would do it one way, however. Well, R would do it one way. It would be based upon a model formula, almost always, and then it would, it would use a model formula like y tilde something, and it would be some model, and then it would use some sophisticated modeling technique like the QR decomposition and so forth. So R isn't going to do it the way I'm having you do it, but I'm having you do it because it's this way, because it's you have to know quite a bit of the internals of how the modeling is done of R using a QI decomposition and so forth to do it the other way. Although it's probably something you should know. One of you told me that you didn't know what a model mean is, or what a least squares mean is. And a least squares mean is a model mean, which means that the means are estimated from the model, not directly from the data. And I gave an example. I can't remember which chapter now. Well, it doesn't actually matter so much. So do I have a jump file here? No, that's not a good example. Here I have. Can't remember where I am. I'm in section 4. Oh. Well, I know what the problem is. This could be a method because there's a space here, and its best guess isn't good enough. Let me find another example. This was not imported correctly because of the space in your data. That's why a lot of times we don't leave spaces, in variable names. This is not a good example because it's a block design and I don't have replication, but if I have subjects in treatment and I have time, I have 3 treatments, and this is a block design. Each treatment is done on each subject, and I say fit model. And so if I take time as the response and then subject and treatment, and I would probably define subject as a random effect because I'm randomly selecting subjects that I apply the treatment to. So if I run this model, let's see, how do I get this? No. This is not a good example because, but they call it the least squares means. And so you might say, well, why don't they just call it the means? And in certain cases, and if I would have done another case, there would have been another column here that says means. And the means are not necessarily the same as the least squares means. The least squares means are the model means, which are estimated from the parameters. And it turns out that if I have a two-way table, let's say I have a factor A and a factor B, so I have a two-way analysis of variance. And so think of it, suppose I have 3 levels of A and 4 of B, so I think of it as a matrix that has 3 rows and 4 columns. So, and let's suppose I have 3 observations in each of the 12 cells. So I have 3 rows, 4 columns. The rows correspond to the levels of factor A, and the columns represent the levels of factor B. So you could think of them as A1, A2, and A3, and B1, B2, B3, and B4. And suppose I have n observations in each cell, or maybe n is 3. So you can compute the mean of each of those 3. And those are called the sample means, but they're not the model means. In this case, actually, they would be the model means because the sample sizes are the same. But suppose the sample sizes in those cells were different. So the 1,1 cell had 3 observations, the 1,2 cell had 4 observations. The 1,3 cell has 2 observations, and so forth. Suppose the cells are not equal. Now if I compute the sample means, they are not the same as the least squares means. The least squares means, also called the model means, are estimated from the parameters. And if you had a model, mu plus alpha sub I plus beta sub j plus alpha beta ij as the two-way model, then you would get estimates of mu, alpha, beta, and it's based on those estimates that computes the model means. In other words, the model means are computed from the parameter estimates. They are not the same if the design is unbalanced. And a lot of people don't understand this, and so they make mistakes. So at any rate, in your case with a one-way analysis of variance, you don't have to worry about it. Getting back to this, let's look at box plot. So box plot says it's a standard generic, and it dispatches on X. So it depends on what that first argument is. So it dispatches on a single thing. So let's see what happens. So I'm setting generic, and if I do a box plot, it's just showing the same thing. If I show the methods, this says x equals any, x equals formula. So let's just take an example. There's some iris data, which is built into R. I'm going to attach iris. And iris, looks like I'm masking something, but so I'm going to look at let's look at the structure of iris. So iris has it has sepal length, which is numeric, sepal width, which is numeric, petal length, which is numeric, petal width, which is numeric. So it's looking at the sepals and the petals, and it's measuring their length and width. But it also has three different species it's looking at. So it's looking at 3 species of data, and on each plant you're measuring 4 variables. So the this doesn't give the whole thing. Two of the species are Cercosa and versicolor. So that's what the data looks like. So in other words, if I now would plot species versus sepal length, so this one is what? That one is a factor, and this one is numeric. So a factor and numeric. So what do we get if we plot this? What is the default? Well, the default looks like this. It's a side-by-side box plot. So notice the first argument was a factor, and the second argument was continuous. So it gave a box plot side by side. What happens if I interchange the argument? So the first one is a continuous, and the second one is a factor. It gives this. Now that's a valid plot. By default, the levels, even though if you look at the structure, the formal, even though the levels are Cercosa, versicolor, and there's one other, the formal levels are actually 1, 2, and 3. Those are called the formal levels. It's still a factor, but what are called the formal levels are 1, 2, and 3. So what it does now is it plots the formal levels, but it's now segmented in the 3. And that's probably not what you wanted. What you probably wanted is a sideways box plot. You probably wanted the box plot rotated. Well, the problem is it only dispatches on the first argument. So if we could dispatch on the first 2 arguments, then we could define a sideways box plot without really doing anything new. So in S4, we can do this. So in S4, I'm going to set a method. I'm going to set a method that dispatches on both X and Y. And the box plot is X tilde Y. So this is one method. And now I'm going to do it again. I'm going to do plot, and notice up here the signature. So I said set method plot, X is numeric and Y is a factor. Okay. So this is sort of the standard thing that happens when you do a box plot, and what we did before when we had species first, because species I'm sorry, this is the reverse, but this is having X numeric and Y as a factor. The one I'm doing now has X as a factor and Y as numeric. So notice that the signature here, as I'm reversing the roles, if X is a factor and Y is numeric, okay, it does Y tilde X. If X is numeric and Y is a factor, it does X tilde Y. So if I now do show methods, you can see what the options we now have. X is a factor, Y numeric, or X is a numeric, Y is a factor. And now if I do the same one where the first one was a numeric and the second one is a factor, let's see what happens now. Now we get, whoops, wrong way. Now we get that. By the way we dispatched. So we, just by defining it as an S4 class, we could sort of reverse it. You can't do that with just based on the S3 classes. But here we can dispatch on multiple arguments. So we're dispatching on X and Y, so I can look at both X and Y to see which one's numeric and which one is a factor and adjust accordingly. Because fortunately, the box plot does have a horizontal option. Okay. So at any rate, this gives you a little bit more insight into S4 methods. So you should study this carefully. And I'm going to explore, as I said, I'm going to go on to Chapter 4 now today. And I'm not going to spend a lot of time on Chapter 4. It's sort of input-output methods and things of that sort. I'm going to cover some some aspects of that. So we're not going to spend a lot of time on Chapter 4. We probably won't finish it today, but then on Monday what I'm going to do, assuming that I decide to do S4 as your next assignment, I'm going to give you another example that's more related to your assignment. So, and then we'll probably finish up what we don't do in Chapter 4. And then we're going to be moving on to a more important chapter, which is in Chapter 5, which is manipulating character data. And you may say, well, why is that important? Well, think of it this way. What is the genome? Okay, when you're looking at genes, there's an alphabet of 4 letters. So we have to be able to manipulate. We have an alphabet that has 4 letters, and so when you're doing genomic analysis and doing sequence analysis and things of that sort, we have to be able to manipulate these 4 letters. We may have to search for patterns and so forth. And so Chapter 5 becomes a more important chapter. So I'm not going to spend a lot of time. There's certain chapters that are going to go very fast. 4 of them is one of them. Chapter 4 is one of them. Now, I haven't given you the notes yet, but I will. The notes are not particularly complete, so I'm probably going to add a few things to them before I put them up. Okay. So I'm going to go into 523, Chapter 4, and actually I want to get rid of this because that was something I downloaded. So I'm going to look at this particular file. I'm going to set, actually what I'm going to do is get rid of the graphics. And I'm going to clear, what's happening here? I'm going to clear the console just to start over. Then I'm going to set the, trying to clean everything up a bit. Set the working directory to be Chapter 4. Workspace should be clear. Okay. So I'm going to knit this, but I'm going to mainly step through this. So we're going to look at input-output in R and look at some basic file handling. Yeah, we don't have too much time to do this, but we'll get started. You know, this said set working directory. Well, how do I get working directory? It tells you where you are. Now that looks different, but it's not. You notice the first one says /. That says starting at your home directory. Set it at your home directory, and then it sets it down a couple down the hierarchy. Within my home directory, it looks at, Unix calls it directories, and you know, PCs and Macs tend to call it folders, but same thing. So the subdirectory of my home directory, I have a courses, and then I have stat 523 and notes, and then Chapter 4. Notice that where we really are, if I look at the full path, we're really on network servers. Mozart is the name of our server, but Mozart actually has several volumes, one of which is called Bays. That used to be a server Bays, but then we got a new server and we made what was on Bays, a volume on this more general server called Mozart. And then we have J. Harner courses. And so notice the last part, J. Harner is my home directory. So it's the same thing. This is called the absolute path, and the one above is the relative path. So it's a little bit of Unix. Now, if you're used to a graphical interface, then of course, I've actually mounted his Mozart right here, and so here's J. Harner. And so it's a little bit deep. Courses, 523, notes, Chapter 4. Finally got there. That's the graphical interface way of doing things, right? So, and down below, you can see the path. You can see the path I just went through. But actually, since the Mac is Unix, I actually could go to a different level of this machine. It's sort of by default when it's showing you the file system, it doesn't show you what's below it. But if you know Unix, you can do it on a Mac. You can actually see what's below it, and you see all these other levels that are organized as a Unix file directory. What's below this? So if I brought up, I actually could do it graphically, but if you bring up the terminal, then which now it's a regular Unix machine, you can actually see those other levels if you would want to. But notice it starts out at J Harner. That's called my home directory, and so it starts out. And if I, for example, if I do an ls, it lists what's in my home directory. And if I do an ls -a, it lists the hidden files. Everything that starts with a dot is a hidden file in Unix, and so all of these files are actually hidden. But these are nonetheless. Here's a file called .aura-data, and .aura-history, which holds information from Aura. That's if I run Aura and I use sort of my workspace is in my home directory, then those items are put in .aura-data. And the .aura-history, if I ran from the home directory, the .aura-history is the history of what I ran, and so forth. So at any rate, and if I give a more complicated command, you'll see that all my directories have certain permissions, which basically means that you can't get into them. So if you try to go into my directories, unless I've opened it up to you, you can't get in. So I sort of have this isolated environment, as do each of you. So I can't get into your directories, and you can't get into mine. It has strong protections against that happening. But I can actually open up a directory to be public if I want to, which means that anything I open up, you could go in and look at. But I'm a little cautious about what I do that on is. At any rate, so that's set directory. Now, there's a system.file. There are system files that exist, and suppose I want to know the system file for the package bioinf. This is a package in bioconductor called RI-bioinf, and I think we've looked at that file before. So if I create that, and I'm not sure what's in that FP. Yeah, so that's telling you that it's in user lib6. Now remember, you got to think of this. You got to start thinking a little differently here, not like it's your local little laptop. We actually are on a server called RStudio, but you have a directory that's based. You're in some other directory that's in Mozart. But we take your home directory and mount it on this other server so that you have access. If you're using SAS, you're using another server, and we mount that same. You have the same directories and data, and you can mount it on different servers. So you always have. It's not as if you're on this server you have one set of data, on another server you have another set of data. You have a common place, but everything is there, and you can mount it on different servers. We automatically do that for you. So when you log into RStudio, it automatically mounts your home directory on RStudio, so you have access to your files. Otherwise, on every server, you would be creating new data, and then you'd not know what's on what. Now that's a little bit of a problem if you're using multiple desktops. If you have a laptop and a desktop, you now have two machines that you have different files on one and different on the other. And then you say, well, I edited this file, and I don't know which is the most recent version of the file. Is it on that machine or on this machine? Now, there's one easy way to solve that problem is if you do everything off Dropbox. If you always work on Dropbox, again, it's a file system that's in the cloud, and it's common to any machine you walk into. So you have an account that's Dropbox. Well, you can do it in the cloud in a browser too, but you have an account that's called a Dropbox account, and you can mount that on this machine, on that machine, whatever you want to. Anything I have an account on, I can mount those files. if I don't have an account on that machine, I can do it through the cloud, through a browser. So that Dropbox sort of gets around the problem that a lot of people previously had. And there are other systems too. It's just I prefer Dropbox. But at any rate, let's look at F1. If I run F1, I'm opening this file, and I'm going to read lines from F1, and it reads this. So I'm actually reading from the file F1. So basically, I opened a connection to F1. And this said I only have permission to read, not write. So I can read FP, and I'm going to read it. I'm going to use a function called read lines, and it reads it. And now what I'm going to do is close F1. So I basically opened a connection to the file that lets me read it, and then I'm going to close it. So this took a file on the system, on the server, and it let me read from that file. Okay. Now, you can also do that over the internet more generally. So I could read files. There are various ways that you might be able to do it. Now, in this case, I'm just doing it on my own system, but if you want to read files over the internet, there are other ways we have to do it. I forget what the scan does. Scan is another function. Oh, yeah, the scan is another read function. Read lines reads line by line, whereas scan lets you scan a whole file. There are various options you can do with scan. It's just another way of reading. So the scan function is sort of more general. Suppose I want to know, well, where is, I'm looking at our home for doc. So let's get the file path. The file path for doc, starting from our home, is user lib64r. So that's where r is, and then it's in a directory called doc. Now, if you brought up the Unix command line, you could actually look at this. And R actually lets you bring up the Unix command line. Let's see. Where is it? I forget. I don't do this too often because it's a little bit awkward. Shell. So if I bring up shell, this actually brings up a Unix command line. Bash means the bash script. That's what's called a shell. The SH means shell, and BA means born again. Originally, when Unix was developed, there was a shell script that you could actually write Unix commands in, and then there have been tons of iterations of this shell script, and they each have different sort of properties. And Bash is called born again shell. Obviously, there was previous versions of this. So, if I do ls now, this is giving me the files in this current directory. And so that's just the ls means list. Unix commands, like if I change directory as cd, I won't do that, but at any rate, if I say cd slash, that would take me to the root. Again, I'm not going to do that now, but so this gets into this a little bit. If I ask where is bioconductor, the bioinf, where is that package? It's user lib64r library, and that's where this package is. So if you were wondering, at some point, I don't have time today, but if you ask, like on the Mac, if you install packages, so if I brought up sort of the standard environment for the Mac, which I don't seem to be finding right here. If I bring up this and I go in and I say I want to install a package, it will ask you where you want to install it. And there are two places it can install it. It can install it in your home, in your directory, or it can install it at the system level. If it installs it at the system level, anyone who has an account on my machine here can get it. If I install it under my account, only I have access to it. So you get a choice. I usually install them at the systems level, but that's because my account also has administrative privilege, which lets me install it at the systems level. Now, if you try to install a package on RStudio in the cloud on our server, You can only install it locally. You cannot install it. That's why I have to have Steve Giesler do it, because he's the system administrator, and only he can install it at the system level. If he installs it at the system level, you all have access to it. If you install it, no one else has. Only you have access to it. But if you're missing a package, you can temporarily do that. You can install it yourself, and it's in your home directory, but it's in no one else's, because you don't have permissions to install at the systems level. So this is a little bit about Unix. Now this, what I'm doing is, if I set working directory at r.home, okay, so that would be setting at r.home. So if I then say get working directory, except I misspelled it. You see, I'm now at the R home. Okay, so at any rate, so I can list, if I say list files where path is doc. Now you might wonder if I say list of files that are in make, then the way things are, there's nothing there. So you might say, well, why is that true? So if I look at the shell, and if I ls, let's see, what am I not getting? Yeah, print working, PWD means print working directory in Unix. And so I'm not sure where it's finding doc, but it's not finding, make is not here. So it's not finding anything, and so I'm getting, now on his system, he obviously had it organized a little differently, because on his system that probably worked. But make is something that will be someplace within the Aura hierarchy, but it's not on our machine, it's not where it is on his machine. Okay, so I'll just do this one and then we'll quit. If I set working directory to be, it's not letting me. That's indicating maybe it was not permissions. Interesting. Oh, that's right. Doc was, what happened when I did doc? Okay. I need to look at that, because here it says doc is here, but it's, when I looked at it, it didn't see it. So let me stop here and look at this code to see what's going on. This was what he did on his machine, and when you install Aura on different systems, it doesn't always put everything in exactly the same place. So what might have worked on his installation will not necessarily work here. And that's why there are certain things that are standard, though. The things that say system.files, they tend to be standard, because those are things that we often extract in, but other things may not be in the same location. So I'll stop here, and we'll do a bit more on this. I'm not going to get carried away with this. I'd rather spend more time on the character manipulation in Chapter 5. But we'll cover this a little bit more on Monday.